Hello, good morning, good afternoon, good evening. Welcome to our developers conference, to another session at the automotive section. Today we're going to talk about automotive safety with our Lattice FPGAs. My name is Christian Müller. I'm the system architect at Lattice for Automotive. I joined roughly 2 years ago. I'm been in the industry for now around 9 years. I've been previously with Intel, where I worked as a field application engineer and a technical specialist as well in the automotive domain. And here with me, I have Harald Friedrich from UTech, who will present this section and go as the expert on the topic. And I will hand with this over to Harald. Thank you, Harald, for being here today.
Thanks, Christian, for the very good introduction. I'm going to shortly introduce myself. So I'm working as a consultant in UTech. I do have a long experience in electronic design. So I studied electronics, worked in different industries, moved to the application support for FPGAs and microcontrollers in the semiconductor industry. And in this role, I dealt with different applications already involving functional safety, also in different markets. And with UTech, I'm working with a company that was founded in 1986. It's a company that is based in Germany, so in the middle of Europe. And as you can see, we're serving customers worldwide. We are owner managed. We do have different locations in Germany. And by this year, we will have a turnover of over 30 million with roughly 300 engineers. And we are doing mainly customer designs and also consulting for functional safety in all the areas that are basically driven by regulations. So some of the standards that we do support in the functional safety area are for the different standards. The base one is ISC 61508, which is the overall standard for safety. And derived from that, we see the automotive standard, the ISO 26262, and that is the one that we are focusing on today. But as UTech, as I said, we are working with different standards, different industries. So we are in the machinery, we are into avionics, we are into medical, and all kind of applications. And this is not only for functional safety, but also for embedded electronics. Now, going to the automotive world, I think Lattice have a very good footprint into the automotive applications. And you see here some of the applications that you can do with Lattice FPGAs. Some of these functions, FPGAs can be used to be very flexible and easy to integrate functions. And majority in the past, at least, did not require functional safety for the integration. But now with emerging technologies like autonomous driving or assisted driving or the e-factory, e-mobility topic, you see there are bridging and sensor fusion topics that come up to really decide whether or not it's safe to go somewhere. For battery management, we all know that the batteries can inflate pretty fast, and therefore you need to take care that this doesn't happen. So there are some safety requirements popping up that we want to discuss today, how to fulfill them and how to get FPGAs into safe designs for automotive designs. So what does functional safety mean in general? So functional safety is applicable only to active systems, but that's especially in the electric or electronic or programmable electronic systems. So everything that has to do with these kind of active systems. And functional safety is there to protect people and the environment against faulty systems. So it's your protection. And as you can see, here's this example with a passive protection. That's also very essential to save life, but it's not part of the functional safety definition that we are talking about, but we are talking about the functional safety that is relevant in electronic systems. And functional safety itself means the capability of a system to enter a safe state and remain in that state once there is a failure in the system. And these failures can be arbitrary as well as systematic. And by design, we try to avoid systematic failures as much as possible, but still we need to be able to react to any kind of arbitrary or random errors. And so from a development stage, we can try to make it as safe to avoid systematic failures, and I will then discuss how that is done in a second. But also for the random failures, we need to be sure that the system goes into a safe state once something happens. So what you also see here is a conflict of interest, because we sometimes talk about safe systems and we talk about security. So the major difference between safety and security in this definition is that safety is for protecting people of damage, and security is for protecting the assets and the knowledge and the know-how and the data from being corrupted. And sometimes there is a conflict of interest, because if you want to make something safe, you don't want to change anything in the system. If you want to design for security, you also need to take care of new threats that might occur. So changing a system might be necessary, but for safety, you don't want to typically change a system. Therefore, you have a conflict of interest, which needs to be taken care of. And that all is reflected in the complete overall development effort. So what is the system about? I here show a system that has a control unit and it has some sensors. So the seeing, measuring, recognizing part, and you have the outputs, the actuator, the operating part, what needs to be done if something is calculated. And that's how we typically design such a system or define such a system. So we have inputs, we have the control units, and we have an output. And now I talked about the failures that might occur. And from the systematic side, we need to make sure that if a sensor is not there, or we need to have enough sensors to make a safe reaction to do some execution. But that can be done by system and system design. But for random errors, we need to take into consideration what might happen to a sensor. And therefore, we need to look into different topics. And so, for example, the system needs to work under all specified operating conditions. So that can include different temperatures. So inside the specified temperature range, the system needs to work effectively and correct. There can be mechanical damage. So especially in a car, when you drive and have an accident, there is some or potential for physical damage. In one case, for example, the sensors don't work anymore. And then for a BMS system, battery management system, you need to take care that the battery doesn't go up into flames. Also, the simple problems might occur, that oxidation of contacts can come, or that the power supply is not working as intended. So that's all topics from a system level that needs to be taken care of. And now when you look into more details of what might go wrong, you need to look into every single aspect of that overall system. So you need to look into the sensing part, what might be wrong. If you have a camera sensor or a LiDAR sensor or just a simple switch, what can go wrong to this sensor input? Mechanical influence, aging over time, or even the external shield causing reduction in sensing. Might be snow that limits the view of some systems. And then if you make sure that the sensor is working, you need to make sure that the connection to your ECU is working correctly. So again, an aging of hardware is an important topic. Also missing mechanical protection or wrong dimension. So very simple errors that can be a disaster in the end. And from a systematic point, you can take care that everything is working from the beginning correctly, but you still need to care about the arbitrary or random failures in these systems as well. So we also need to look at the control unit, the ECU, what could go wrong. So if the signals are coming into the ECU, then there can be hardware going wrong and software going wrong in the processor in the FPGA that takes the calculation. So from the system, you need to make sure that from the connector to the calculating device, the devices are working correctly. So if you have a wrong dimensioning of a resistor in the easiest way, could make the system go wrong or decide for wrong values. And in the CPU, there are some features that can happen. You can have bus errors in the system that you need to take care of. And in the software also, if you do calculation of these functions. Or sometimes the response time might be too long, and that you can take care of systematically by defining what kind of response times you can achieve, and then everything should work correctly. And the last thing is that the actor also can go wrong. So in that case, we see here a brake system. If the brake mechanically doesn't work anymore, you still need to make sure that the car doesn't drive into other cars or into people. Unwanted movements is something that you need to avoid. And also high voltage can be a problem. So what if there's some defective insulator or something like that? So that's all the topics that you need to take care of systematically, as well as to take care of the random errors. And now, to avoid the systematic failures, there are some standards that allow us to develop according to safe development processes. And with that, you prove, or you have a structured way to avoid any kind of systematic errors. And for the automotive world, that is described in the ISO 26262. And this development process you see here, when you're familiar with the safety process, you have probably heard about the V model. And that is represented even in the standard. So you see here big V for the systematic approach to design an electronic design. So the systematic approach is that you go typically from your risk and hazard analysis. So you see what can go wrong in a system, and you derive your safety goals out of that. And then you go all the way from the system requirements to project plans, to top-level designs, to detailed hardware and software description, to the real implementation and development. That is in the bottom of the V diagram. So this left part of the V diagram is all about requirements and doing the development. And then going that way up to certification again. And here you do all kind of module testing, verification, validation, to get in the end the certification for your product that is safe. And this needs to be done as well as on a complete system level. So if you're building a battery management system, or if you're building a camera application or LiDAR radar system, that needs to be done for the complete system level. And then it's split into hardware effort and software effort here. And as you see, it's all directly represented in the standard. Now, besides doing that development according to the standard, you also need to take care of your systematic or management processes that need to be in place in your company. So not only does the development flow need to be presented by that process, but you also need to have all the management processes in place. And that typically involves like a functional safety manager that needs to be there. And the standard also says for something about supporting processes, which can be there. So a lot of organizational topics that you need to cover, and then the design flow. And with this design flow, we try to avoid all kind of systematic errors. And I think that's the most important part. Now, when we go for a real system implementation and we want to design an ECU, that's typically where FPGAs have a very good play in, we can have different approaches for doing such a system. So one way is an example for an ADAS application. And in this example, we see camera or image sensor inputs that go into an FPGA that does a lot of pre-calculation, and then together with an application processor or SoC, this complete system here needs to be safety qualified. So this is a typical implementation of a two-chip approach, where we have one device that does some part of the logic, and we have another device that does other calculation. And the safety is typically split about these two devices for a certain safety requirement. So that's one approach for having that two-chip approach. And then there are other applications, like more simple ones, for example, a motor control, where the FPGA can do all the motor control functionality from the inputs coming from an external control unit to doing all the functionality that is needed inside a motor, and then directly driving the physical network drivers as well as the motor control to the PWMs. And here we have one FPGA doing the complete logical functionality. And so we see two different approaches, one as a two-chip implementation for the logic part, and one as a one-chip implementation of the logic part. Now, what the good thing is for the ISO 26262 process, when we have a two-chip approach, the standard allows for so-called decomposition schemes. And with this, if I want to achieve a certain safety level, and in automotive world, the safety levels are called ASIL A to D, where ASIL A is the lowest safety level. If you have already a safety level, if non-safety level is required, you typically call them QM designs, so quality managed designs. But as soon as you go into safety integration levels, then you can do a decomposition of a system. And you see here the overall requirement is your system needs to be ASIL A. And if you have a two-chip approach for that, you can decompose it to having one design fulfilling the complete ASIL A requirement, and the other one ASIL, no ASIL or QM designed. And these two devices together then build a system that is ASIL A compliant. And the same decomposition scheme can also be done for higher safety levels. And I skipped the B and C integration, but go for the highest ASIL level in automotive, which is ASIL D. And here you see there are different possibilities to reach that. So one possibility is that you can have an ASIL D design by using one component where, for example, the microcontroller is already ASIL D designed, and the accompanying FPGA is only using QM, so not being certified for being used already in ASIL designs. And these two chips together then build an ASIL D system. Or you can do it with two devices being ASIL B qualified, so none of them having the ASIL D requirement itself fulfilled. But these two devices then build a system which is ASIL D compliant. And that's a way where if you have a two-channel approach, you can use non-qualified FPGAs in a safe system if, for example, the MCU already has the required ASIL standard, which is in many cases the topic. In automotive, there are some suppliers that are very big in doing pre-qualified devices like Infineon, Texas Instruments, NXP, Renesas. They all have these controllers that already have a certain ASIL certification. And with those, you can use an FPGA without any other worries. Now, what do you do if you want to have a design where you don't have another component that can help you to do that ASIL decomposition? Then you the standard requires or wants you to use a pre-certified device. And as the current Lattice implementation is not yet qualified for being used in automotive designs, we can add that qualification and that proof that these devices can be efficiently used in a safety design by doing the hardware evaluation approach. And in the safety world, there are different classes of hardware elements. And to do that evaluation, that's a step that needs to be taken if you want to use an FPGA in an ASIL-B or ASIL-D design. Then you can use that sort of easily when you do that evaluation. And that evaluation approach, that's something we do and did for customers already. That is, you need to prove that the device can be used. And there are different device classes. So if it's a class 3 device, which is typically the case when you have a lot of functionality inside the device, then the standard typically requires that you use a pre-certified device. And if you don't have a pre-certified device and you classify it as class 2, which you can do if you provide additional field reliability data from field experience, then it can be classified as a class 2 device. And a class 2 device you can qualify and evaluate that it is to be used in a functional safe environment. And with that, a notified body will state that this device can be used just as any other pre-certified device for in-context development. And that is a very good point, because then you can still use FPGAs easily, even in a single control unit implementation, when you just use one FPGA, and you can achieve ASIL-B, ASIL-C, whatever is required for your design. And you see here that this evaluation is widely independent on the required ASIL level. So to do that kind of hardware evaluation, there are some steps that are necessary. So from the classification, requirements, analysis, and I'll talk through that over the next slides. So the certification, as I said, that's the important part, that the standard allows you to use a non-classified device. That is by defining that it's class 2, or by proving that it's a class 2 device, and that can be easily achieved by providing additional reliability data and acceptance test procedures. And the good thing is that Lattice is very, very helpful in providing that kind of data. And therefore, with the assessment bodies, it's pretty easy to walk them through this process. So the next steps after the classification is the requirements phase. And here, the customer needs to state all the safety functions that need to be implemented in a system. And that is basically independent of whether or not you use a certified or classified device, or you use a QM device. You need to take care that all the safety functions are specified. And even if you used, for example, a pre-certified device, you still need to do that to prove that all the functions that you integrate into your system also follow these guidelines. And the safety requirements must be specified for that given context. So the good thing about the evaluation approach is that this evaluation is already in the context of your end application. And compared to qualified devices that are basically out of context safety qualified, you need to have a lot of assumptions that will take place. In this case, we go to the real evaluation context of your system And Lattice then will provide all the necessary information that are needed for the safety functions. and they already have safety functions in the QM mode integrated. And we only need to prove that these are also valid for use in an ASIL qualified device design. So after the safety requirements, we then need to go into the analysis mode. And here we need to see what kind of failure modes are there and how can they be distributed, especially the random hardware failures that can happen, and how the reaction on these can be identified. So we need basically to prove that if there is an error in the real world, that the system reacts accordingly. As we don't know what kind of errors will occur, we need to do some testing, and we need to do, for example, inductive injection of errors to see if this device behaves in the way we want it to behave. And sometimes it's also about the reliability data that can be used to minimize that kind of testing effort. But this analysis is quite important to really go for an evaluation plan. And this evaluation plan then is to describe everything that is necessary to be tested and to be assessed by the assessment bodies. And we will see that all identification and that the device that we are going to use is really identified. So it doesn't make sense for that kind of hardware evaluation if we start that process before the device is really fixed. So once we know what kind of device is there, we know what kind of functions will be used, and we need to specify in the environment what kind of functions are intended to be used. And we also need to take care of the tools and the equipment, not only on the FPGA level, but also on the overall system that are used, and if this is safe. So this evaluation typically goes for the device itself, but then it also takes into consideration the complete system approach, because that's pretty essential as it's an in-context evaluation of the device. And then of course we need to specify the pass and fail criteria, and these needs to be aligned with the assessment bodies. And once we have the evaluation plan, we can go into the test plan. And then the test plan, that's what needs to be done to really prove that the devices are safe to be used in that safety design. And again, we need to describe all the functions. We need to allocate the safety requirements. We need to specify the number and the sequence of the tests to be conducted. And of course, the traceability between tests and safety requirements. But that's a way that needs to be done for all kind of following that V model. That's a standard in safety designs. And the most important thing is, again, the pass and fail criteria that we need to come up with to really see if the device can be used. And if we give all the numbers that were defined in the evaluation plan and the test plan, then we finally get to an evaluation report. And that evaluation report basically summarizes all the tests. And we get a documentation of all that is done. And with this evaluation report, we are sure that the design of the device, the selected device, even if it was not pre-qualified, can be used in that safety design. And that's basically what we want to achieve. So that the end, after that evaluation process, we have a device for this context that is as good to use as any pre-qualified device. And it's an additional step that is necessary in this case, but it's still a pretty easy way to use devices that are not qualified. So especially in the newer Lattice device family, which is very good to be used actually in automotive designs. They are on the market for the last 3 years, or the market introduction was, I think, in 2020. And so they have enough proven quality data, but still it's long enough on the market to be used in automotive applications for the next couple of years, which is also a very important point, to have a system and device selection that can be produced for your intended time. So I think that evaluation process is very important to qualify devices. If you want to go for a one-chip solution with an FPGA that was not yet qualified, you can skip that step probably if you go for a two-chip approach, where you, for example, have that MCU that already is ASIL qualified to that level that you want to achieve with the decompositioning. And then what I'd like to show you here is the safety flow itself is much more than just having a safe device. And I think that's important to know, because when you look for the complete system overview, you have different steps to do. So the first thing is you need to know what kind of requirements you have for your products in general. And this is on a system level. So again, if you do a BMS system or LiDAR system or radar or camera system, you need to know, first of all, what kind of safety level you need to achieve, how is the system spec done, and what are the requirements of your safe products. And once you have that, you need to work out a development plan to see what steps are needed. And in the concept phase, we typically start with a safety plan. So we need to see from the hazard and risk analysis, there are the safety goals that are here, and that then needs to translate into a safety plan. And the safety plan includes verification and validation plan and a lot of technical documents. When you go for a typical design, then you want to have a demonstrator pretty early that is not yet specified, but you want to show probably to your end customer something where the design already can be demonstrated from a functional point of view. And to get to a prototype, which is typically also still untested or uncertified, you go that way doing already the overall safety requirements and allocation. You do the system setup, you go into hard and software features that need to be implemented. And you go for the PCB design, you go for the software components for single software units that need to be safe, and you need to test them again. And so this is basically the way from the V diagram that I described on the left side to the bottom. And here you have a hardware that is designed according to the safety standards, but the testing is not necessarily yet done once you do a prototype. And then the right side of that V diagram, that is all the testing. And this is typically from a timing as long as this initial process. So this side, where you do all the module tests, the unit tests, everything, that is all the necessary part to get to a certification. But that needs to be done under a system level approach. So not only testing that the device itself can be used, but also that your system measures are taken in the correct way. And NewTech is a company that could help you in any kind of these processes. And I'll show in the next slide what is the time and cost savings if the supplier already did something according to the safety standards, and if you use someone who is experienced, or if you have those resources in-house. Because what you see here is, again, a different representation of what needs to be done to get to a safe design. So here, when we do a design that is functional safety in a design where, for example, we use the Lattice FPGA as a single ECU unit, then we need to do the overall safety requirements and specify those. We need to prove that the hardware and the tools are qualified. We need to implement safety functionality. We need to implement safety diagnostic functionality. Need to do all the testing, validation, and verification to get to the certification in the end. And not to forget, of course, the application-specific hardware and software development that we will do. So when you use a supplier that already did something to get to a qualification, and this can be like Lattice did, not being qualified, but using already a QM device where they have safety functionality included and diagnostic functionality, we need to prove that with the evaluation, in the case of a single chip implementation, that these tools are safe enough to be used. And with the information that we get from Lattice, this is already reducing the time drastically and it making it possible overall to be used. And also Lattice implemented some safety and diagnostic functions already. So in implementing the functionality, that is already a reduction in time. It typically doesn't help on the overall safety requirements. It doesn't help on your application-specific development, and it doesn't help on test and validation verification, and not on the TÜV certification. But taken the information and the functionality that Lattice implemented with not being qualified for safety with a stamp from assessors for being used in an ASIL B or ASIL D context, together with the evaluation that we just described, it already reduces the time to get that done. And now, if we use qualified devices, and especially if we have the system context around it, that reduces even more drastically the time. And for example, if you know what to do and you know how to do the safety requirement specification in the right time, that is much better than if you have unexperienced guys working on that. Once the devices and the tools are qualified, we cannot do much here, but from a system level, we can implement, or we know what to do in safety functionality and in diagnostic, what needs to be added. And so we can here reduce the time and also for the test and validation. And in our way of dealing with customers, as we already include the assessors pretty early in our discussions, that saves time overall in the certification, especially if you save iterations. So we believe that we can save up to 30% of time and cost using not only pre-qualified devices, but also with the safety expertise that, for example, we can offer. So I think that's one of the biggest advantages in going or using pre-qualified devices and having the enough experience to use those devices. And also with a system split, if you go for the more complex systems where you have one FPGA together with a pre-qualified component and to do the system setup in the right way, I think that's also very essential from a system perspective to integrate more than one device into a safe applications. So overall, as a summary, I'd like to say that Lattice FPGAs are a very, very good fit for automotive projects that require functional safety. If it's a two-chip approach with an ASIL decompositioning, it's pretty easy. You can use the devices as is and do a design, and you always need to look into all the system things, what I described. So functional safety, design, and development is a complex topic, but it's a topic that can be done. And the good thing about FPGAs is they are easy to use and they provide a lot of flexibility and scalability. And especially with the emerging markets like autonomous driving, like e-mobility, that is very, very easy to upgrade the system over time. And these scalable systems, they fulfill today's and tomorrow's requirements. And what is very essential is that safety and security by design is the most important thing. So you need to talk about it to all relevant people. And not only safety, which we described today, but also the security topic is very, very useful. But the good thing is, you see Lattice, you see Christian on the screen again, you see me. So there is help and solutions available that can easily be used. And I guess you probably know your Lattice contacts. If you want mine, let's see them here. So with that, I'm done. And time for questions and answers.
Yeah, thank you, Howard, for the great presentation and the deep insights into those. Nevertheless, we have received a few questions on the chat, and I tried to group them together, and so to be going through them in a bit. So one of the questions, when early on you presented on the different standards you're supporting at NewTek, one question the audience raised is like, why are there so many? I mean, you talked here about the Automotive ISO 26262. However, there's many other standards, and so why are there so many? And B, do you see that there's maybe a consolidation or any more alignment happening in the market?
Yeah, so I think the 61508 was one of the initial standards for functional safety, and then for automotive, this was basically taken as a base but added to the automotive requirements, and it was defined in a new way. It's a different market being automotive. You have different use cases. So typically when you drive a car, it's not on 24/7, but you always switch it on. So there are different use cases and requirements according to that. And the same applies to the other different standards and markets. And therefore, each of these markets derived its own standard out of that. And the good thing is they are looking what the others do. So when, for example, the automotive standard does something new, which seems to be more efficient to be implemented, then this is sometimes even applied in the other standards. I currently don't see a real effort to consolidate them and to have one main standard, but there are also C-level standards behind that. So you have a special standard for a keyboard that needs to be safe, or for radar systems. And these are all derived from the big standards. And typically these other standards refer to the others, but currently I don't see that they are being consolidated to one big standard.
Okay, thank you, Harold. One other question we got is, obviously when we look at it as engineers or project managers, from a design perspective, the safety design flow you presented seems pretty complex, right? There's a lot of steps, a lot of things to do. So obviously your audience is interested. Is there anything you can shortcut on your side, cut a corner? If you look at the V model, is there any flow what could help me to reduce my actual work I have to do?
Well, maybe I go back to this slide here. What we see in real life applications is that if you follow these process from the requirements to the certification, you need to follow these steps. So there's no shortcut to really eliminate one of these steps. You need to do all the documentation. What we see, however, in real life is that if you follow these steps and you want to get to a certification, before you get to a certification, then they say, well, the requirements are not 100% fulfilled. Did you test everything correctly? So we see a lot of iterations in the process to go really for the certification. And if you do it correctly, that can save a lot of time. I saw a customer where it took him 5 years to get to a certification. He had 5 iteration processes because always he misunderstood, or there was a miscommunication between what was told to be done and what in the end was done. So the assessors always said, well, it's not completely what we requested you to do. And so it was 5 iterations, a very long time. And I think if you do it correctly, that can save you most of the time.
Okay, thank you. A similar question I got here is, so you're showing the slide. I think it's pretty good for that question, actually. When I do have as a customer now my ASIL certified, BD, whatever it is, and I execute any of my code on it, and I put code, right? This could be software, soft IP, or whatever the application is. Do I need to do any other precautions to run this code on this, or can I just simply set up, press the play compile button, and then I'm off, and now I have a safe implementation? Or how do I do that?
Yeah, I think that would be pretty easy. So if I just use a safe device, and I know in the initial phase that was sometimes the assumption that someone tells me I have a safe ASIL qualified device, you just use it, do your design, and you're done. But unfortunately, that's not the case. So when you use an ASIL qualified device, you have some of the functionality. You have proven that the design itself or the device itself is safe. You have a certain set of safety functionality and diagnostic functionality implemented into this specific device. But for your system approach, that's what I mentioned earlier, from a complete system level, you need to see what kind of functionality you use. And the hardware and software elements you're using out of a qualified or even non-qualified device, that's only a small part. So from a complete system overview, you need to check all the implemented functions. And as I mentioned earlier, the hardware and the software flow for each safety-related functions need to fulfill all that VDI flow. So you need to do a lot of testing on each single software component that you add to your safety requirement. And so using a pre-qualified device does help. The same as I described after having that evaluation done. So it helps, but you still need to take care of all the system aspects around it and the complete system safety.
All right, thank you. So it seems I can't take any shortcuts wherever I do.
Yeah, you can save the iterations, and I think that's the biggest shortcut that you can do.
Okay, so switching gears is slightly bit different, because you also mentioned security, and we know security is becoming another very big and important part of system engineering in general, not just for the automotive industry. And you mentioned earlier that there's a slight conflict sometimes between security and safety, and can you maybe share an example where security and safety are conflicting, and how could that be resolved?
Yeah, one of the simple examples that has nothing to do with electronics, but it's a very visible example. So if you build a house or you build a castle, and there are also safety and security aspects. So the safety aspect of building a house is that if you're living inside the house and there's fire, you need to get out of that house as fast as possible, not to get harmed. From the security aspect in that same building, you want to avoid that someone gets in easily and steals all your equipment, all your havings. And in the past, we only had doors that are either open or closed, and you have a lock. And once you lock your door, you cannot get out anymore. Once you open it, you allow thieves to get in. So you had that kind of safety and security issue already there. And now we have doors that can be opened easily from the inside and still are locked from the outside. So there are ways in this case where with a different kind of door open, you can fulfill the safety and the security requirement at one place. I have one slide which I'd like to show. If you have safety and security requirements, and every safe system should have a security requirement, because mainly all the devices by now or components are connected. You have a service interface, you are connected with your camera system to the main CPU. So someone can get into this communication flow, and you need to make sure that your system safety and the security are both considered from the very, very beginning of your design. So when you do a project, you need to have your overall system requirements, you need to have the safety requirements, and you need to have the security requirements. And sometimes, as I said, with that example of the building a house, you have conflicting interests. So the important thing, you need to make agreements in every single development stage. And sometimes it's pretty hard to find a solution which fulfills both requirements. And then you need to decide what is more important. And right now, it's saving lives is more important. So in the end, safety rules over security in general. And the way to fulfill both is you need to look into your safety requirements, into your security requirements, and have them in parallel developing over process. And this slide is also very useful to show that once you have a safety stamp, typically the safety development is done. But for security, the thread goes on. So you need to constantly look into what's coming next from security topics. And so security will be a longer topic that you need to fulfill for your system that you're providing to your end customers.
Yes, super. Thank you very much, Harald, for those insights. Actually, you answered one of the other questions around the safety and secure design flow with the last slide already, so I don't have to go into that question in more details. We do have a few more other questions, but I think we're at the top of the hour. So I thank you very much, Harald, for presenting here, for being here with us today. Also, thank you very much for everyone who joined this presentation. We will go back to you via email or even in person, some of our customers, to respond to the open questions. So again, thank you very much for joining Lattice Developers Conference, and see you soon again when we talk about our automotive devices and in general about our Lattice FPGA portfolio. But thank you very much.
Thanks for the invitation. Good morning, good afternoon, good night to everybody listening, and have a good time.